Great, thank you very much. Great to somewhat see you all. So my talk will be about random interlacements and more precisely local uniqueness. I don't think random interlacements have been properly introduced yet this week. I mean, Piet talked briefly about it, but just briefly. So maybe let me do like a short introduction on what are random interlacements before speaking about more recent developments, right? So maybe the first thing to say is that they were introduced by Schnitzman like 15 years ago in 2010, I mean a bit before, but 2010 it was published. And this motivation was to study the random walk on the torus. Okay, so what this means is the following. You take a torus, and let's call its side length n. And so this is like the torus of side length n on a dimension d. And I will need throughout the talk my random walk to be transient. So I will assume that d is larger than 3 throughout today's talk, okay? And the idea is just you run a random walk on your torus. So first, where does it start? Well, you start it uniformly at random. Okay, so you pick a starting point, let's say it's this one, and then you just walk, okay? And if you arrive obviously at the top, then you reappear at the bottom, you reappear at the top, right? Since you're on the torus, and you keep going and so on and so forth, right? So maybe let me put some direction. Yeah. So for how long do you run your talk? So until, so x, until time, u n to the d. And if you make n goes to infinity, so n is the size of your box, yeah, of your torus, you obtain what is called the random interlacements. So maybe a comment on this time here, u n to the d, okay? So here u is just some parameter that you're free to fix. It would be your percolation parameter. You can think of it like in that way. It's just a positive number. And why do we choose scale n to the d? Because at this scale, the random walk will have visited a positive proportion of vertices, okay? Each vertex has a constant probability to be hit at time u n to the d, and this constant depends on you. And this constant, you can think of it as your percolation probability. If your percolation model will be my random walk visited a given vertex. Okay, so this is the motivation. It is you take a random walk on a torus, and you make it you make the torus go to infinity, and you obtain what is called random interlacements. But random interlacement is not just about the random walk on a torus. You could also look at random walk on a cylinder, or you could look at a random walk with like a boundary condition, and you start your random walk from the boundary. And if you parameterize things correctly, all these different objects, they all converge in the limit to the same object, which is random interlacement. So random interlacement is some kind of natural notion of random walk coming from infinity. Okay. And the advantage of it is that it becomes translation invariant, right? Contrary to the usual random walk on ZD. If you are just doing random walk on ZD, you will need to choose a starting point. So maybe let me be a bit more formal, okay, in how it's really defined. And you will see the definition comes very naturally from the limit that I was previously taken. So formally it's just a Poisson point process. Okay, and what are the elements of my Poisson point process? They are just random walks, right? So the idea is the following. Let's say you fix a set K on your torus. Okay, and then K is fixed and you make n goes to infinity, and you wonder, how does my random walk look from the point of view of K? Okay, so this means I look at K and I forget about like the torus, because the torus goes to infinity, and I just look at the trajectories that hit k. Okay, so I have like one trajectory like that. Okay, and now it's coming basically from infinity, and it's going to infinity here. So this was my very first excursion here, and then I had a second excursion, and this second excursion was just doing something like that, right? And it was also coming from infinity now. So now they are independent because I had enough time to mix, because I was going so far away that I forgot where I came from. Okay, so these random walks are just independent. That's why I have a Poisson point process. And the question is, but what is their law? Okay, so the idea is to say, okay, let's say I first need to speak about a random walk. I first need to fix a starting point. So let's say this is my starting point. So I will take a starting point of my walk from the point of view of k. Okay, just the first hitting time of my walk. I remember there's a direction for my walks, like that. So I take my first hitting time of k, and I look at everything from the point of view of this first hitting time. So what do I see? So this will be the measure now that I'm going to describe that describes the law of each of these excursion. Okay. So one excursion, first I sum over all my starting point. Okay. And then once I know the starting point, what do I look like? Well, in the future, I'm just like a random walk. Okay, so I'm saying in the future, I do something. Okay, this is a measure of the event that in the future, my random walk is in A+. In the past, I do something else. Okay, in A-. But then in the past, I have some more information because I know that I chose X as my starting point of my random walk. So it means that in the past, I never hit K. Okay, so if I call H tilde K of X as my first return time of X to K, not here the 1. Okay, it's the first time I return in K. Then I want to say that H tilde K of the past is infinite. Okay, it's just another way to say that I never come back in X. So in the past, I never return in X. Okay. So this is the very natural measure that arise from my excursion. And now I can decompose this measure into two parts, as I already started to do, which is the future part. So the future part is just Px of A+. Okay, Px is the law of the random walk starting in X for me. And then I have Px of A minus and H tilde K is infinite. Okay, because my parts and my my future, knowing the starting points, are independent by Markov property, right? And now, okay, this is one form you can write mu k. There's maybe a slightly nicer form where you can write it, where you only have probability measure, because my second probability here, it's not a probability measure, because its weight is just a probability that H tilde k is infinite. So for this, let me reintroduce some notion that Pierre already introduced, which is the notion of equilibrium measure. And so what is the equilibrium measure of X? This is exactly this total mass of my probabilities that appear at the bottom. Okay, the probability that I never come back in K. And then once you have the equilibrium measure, there's also the notion of a capacity, which is associated to it, that you also saw previously.
Sorry,
the capacity,
Alex.
yeah.
Seb asks, he missed the
Sorry.
minus and A plus.
Of A plus and A minus, they are just whatever events of the future. So mu k, it's like mu k of in the future, my trajectory looks like A plus, and in the past, my trajectory looks like A minus. So you can take them as I don't know. A plus is just in the first P step, I visit these vertices, and A minus is the same kind of event. Okay, just you can look at it as cylinder event. Yeah. And so the capacity is just the sum of the equilibrium. Okay, so with this notation at hand, now I can rewrite my measure as the sum of the equilibrium measure times the probability that my random walk in the future does something, and times my probability that my random walk in the past does something, knowing that I never come back. Okay, so now I really have two probability measures. It's just that the past is a random walk condition to never come back in K, and my total weight is of this measure mu K, is the sum of the equilibrium measure, and so it's the capacity, the total weight of my mu K. So mu K is not a probability measure, right? It's a measure with a mass capacity of K. And so what is now random interlacement? Okay, so there's different random interlacement things. So the first random interlacement thing that I will introduce is a random interlacement process. So as I was saying, this is a Poisson point process, omega, let me denote it by omega ku, and its intensity is u times mu k. Okay, so u was this parameter that I had before, where I was running my random walk on time u and to the d, and u is fixed, and I go to infinity, and this will be the u that appear in my Poisson point process here. So it's my parameter. And so this is, if you want the definition, let me maybe give a more concrete way to write this. As you may know from Poisson point process theory, one can concretely write this as a sum of Poissonian number of trajectories. How many trajectories I have? I have the total mass of my measure. And as I said, the total mass of my measure is u times the capacity. And then I have delta xa. So I have some, here the xi, they are IID. And they have low mu k. So, okay, mu k is not a probability measure, so I need to renormalize it to be a probability measure. So this is just renormalizing to be probability. Okay, so each xi has exactly the law described by mu k, which was coming naturally from saying I have a random walk that in the past was coming to infinity, eating k for the first time in x, and in the future going to infinity. And the number of them is a Poissonian with parameter u capacity of k. Okay, so this is like, let's say, the definition you should keep in mind. There's obviously something a bit weird here, is that this definition depends on the choice of k, a priori. But this is actually not the case, or it can be made to be not the case. So this is what Schnitzman proved in its initial paper, when introduced random interlacement, is that there exists a Poisson point process omega u, okay, such that if you take omega u and you restrict it to k, then it has the same law as the process above, omega uk, okay, for any k. So by restricting here, I mean a very specific restricting. I mean restricting and rewiring. So I take my Poisson point process. So this is a Poisson point process of doubly infinite trajectories. And then by restricted to k, I mean I only keep the trajectories that hit k, and I start them whenever they hit k. Okay, yeah, exactly as in the picture above. And this has the same law as omega uk. Okay, and how do you prove such a theorem? Well, you need to prove some kind of consistency, and then you use a Kolmogorov extension theorem. So the consistency that you need to prove is that if I take k prime is included in k, then if I restrict omega ku to k prime, I get omega k prime u. Right? This is the thing that you need to show, and this is what Schnitzman showed, and it's true. And so you can make that consistent at all scales at once, and not have to fix a given scale first. Okay? Is the definition clear? Okay. So this is the random interlacement process. Maybe let me also define over. So I'm writing Ri. Ri will be before me random interlacement. I didn't say that. So you have the random interlacement set. So this is IU. And IU is just all the points that are hit by any random walk. So this is the union of all the trace of my trajectory. So W here is just some random walk in my process, and IU is the union of my trace. And then I have also the vacant set. And the vacant set is the complement of the interlacement set. In other words, the vacant set is a set of points which have been avoided by my random walk. Okay. So it's all the points, if I run my random walk on the torus, if you want, that have been not visited yet at time u went to the d. And this is what the vacant set is. And note that from my previous definition, you can recover another way to define the interlacement set, which is maybe less instructive, but that is much easier, which is to say, let's look at the avoidance probability for my interlacement, so the probability that the interlacement avoid the set K. So this means exactly that there's no trajectory that hit K. Okay, and saying that there's no trajectory that hit K, it is equivalent to saying that my Poisson point process restricted to K is 0. Okay, and so this is a Poisson point process, and so the number of trajectories Poisson, as I was saying before, with parameter u capacity of K. And so I want this Poisson to be 0, and probability that Poisson is 0 is just exponential minus u capacity of K. Okay. And so what's nice about this formula is that this avoidance probability for the interlacement, they entirely characterize the law of interlacement. Okay, so I could take this as a definition of the interlacement. It's the unique set that verifies this. Then obviously you need to show that it exists, and this is what Snetsman did. Okay, so if you've heard about interlacement before, in the context of percolation in particular, quite likely what you've heard about is percolation for the vacant set, because it has been studied much more than percolation for the interlacement. And let me do just a small recap of what is known. I mean, I will not be able to put everything, obviously, just a small selection. Like maybe the first question is that the phase transition is non-trivial. And so I'm doing percolation for VU. So what does it mean here that the phase transition is non-trivial? It means that for U large, I do not have an infinite connected component, whereas I have one for U small. And it's the model, the interlacement set, when you increase U, you have more and more trajectory. Okay, so your set increases, but the vacant set, it decreases when you increase U. So you have less and less chance to percolate. So this was proved by Snitsman for one of the bound, and then he improved it together with Sidoravicius in 2009. I mean, the second paper was later, actually. And then you can ask all the usual percolation questions. So for instance, is there uniqueness of the infinite cluster? And this is true. This was proved by Teixeira. Then you can use maybe sharpness. Okay, for instance, is the phase transition sharp? And this was proved by Deminil, Copin, Goswami, Rodriguez, Severo, and Teixeira in 3 big papers in 23. And another question you can ask is the question of local uniqueness. And as you saw, this was the title of my talk. So what does local uniqueness mean? I will define it properly in a second. Let me just say, it means that the supercritical phase is well behaved in a sense. That is that there is really a unique giant connected component. Okay, so not only not only is it unique, but it's unique locally. Okay, so locally, I really see only one giant connected component. And so this was proved, like the existence of a phase for local uniqueness was proved by Drevit, Straff, and Sapochnikov. And then recently, it was extended to throughout the whole subcritical phase by Goswami, Rodriguez, and Schusensko. Okay, so the point is that to show, okay, a lot is known for this model, and it is a lot is known, and a lot is quite similar to what is known for Bernoulli. I mean, not everything is, and there are some differences, especially in the proofs, and they're quite different because this is a strongly correlated model, and you have all the correlation from your random walk that enter your model. But what I want to talk today is not this. Okay, it's the other percolation model is the Interlacement set. So what about the Interlacement set? Because if I just give you the random walk on the torus, well, maybe you will be first interested to in the question of how big is my random walk before asking how big is the complement of my random walk, right? It seems like a more natural question. And it has been studied less, and there's a good reason for that, is that the phase transition for this model is trivial. So why is it trivial? Well, because the interlacement percolates for any u. This is simply because a random walk is an infinite collated component because it is connected by definition. It's a simple random walk on my neighbors, and it is infinite. And so yeah, I trivially percolate always, okay? Because I always have at least one random walk actually, so I percolate. Okay, so that's why it has been much less studied because there's no phase transition. But even if there's no phase transition, you can still ask usual percolation question, but percolation question in the supercritical regime because this is the only thing you have, right? So first question to ask is, well, do I have a unique cluster, right? Because I have many random walks, but are they all connected together? And the answer is yes. And this was proved by Snitman. So we're using a Burton-Keane kind of argument. So you just, all your random walks, they all connect together to form one giant component, okay? And then once you know that they all connect together, you can try to ask a finer question about how exactly do they connect together, the walks. So for instance, you can ask, how many walks do I need to connect 2 points together? So this is the following result. So I can connect any x and y in my interlacement set using at most d over 2 trajectories. So what this means, if you say, let's say you're in dimension 3, okay, so it means you can connect them using 2 trajectories. So it means just x is in some trajectories, y is in another trajectory, and they just touch each other, these 2 trajectories. Okay, so in dimension 3 and 4, it means that any 2 trajectory of interlacement will touch each other, which is actually well known because 2 random walks in dimension 3 and 4 will always intersect each other, 2 independent random walks, right? So this is dimension 3 and 4. This is just saying exactly that 2 random walks will almost surely intersect each other. But then in higher dimension, you can the 2 random walks stop intersecting each other, but you can use, and let's say in dimension 5, you can use one additional random walk to connect my 2 random walks together, okay? So with 3 random walks, you are in dimension 5, you are able to do your connection between any 2 points in your interlacement. And so this is Raf Sapochnikov. Maybe I will speak a lot about papers from them, so let me abbreviate them as RS. And also independently at the same time by Prokech and Tykeson. Okay, so this is already describing quite well the geometry of my interlacement. But this is like some kind of global geometry. And when I'm saying they are connected, it means they are connected somewhere, but I don't know if it's very far away that this connection happened or not, right? And so this is the point of the question of local uniqueness. So what is local uniqueness? Now I have my main definition. So local uniqueness of UR, this means that any 2 points which are in a given ball, are connected together. Maybe not in the same ball, but in a slightly bigger ball. So let me say in B2R. Okay, so maybe let me do a small drawing. So let's say I have 2 points in my interlacement. So maybe it's like a 1 point here, 2 point here. So the smaller box here, this is the smaller box here is BR. Again, this one is B2R. And then I want, if local uniqueness happen, it means that these two trajectories are connected together locally, so within B2R. So maybe I have another random walk in my interlacement that was doing something like that, connecting them together. Okay. I need to give myself a little bit of space here with this B2R, because it could happen that something like this happen, that I have a random walk that barely touch BR and immediately leaves here. And then this random walk, it will typically not be connected to any other random walk in BR, okay, because it is very small in BR. But, okay, in B2R, I will actually have some random walk that connected to the rest. Okay, so that in B2R, I have just one connected component for the random walk that hit BR. Okay, so this is what the picture looks like. And maybe for those who know about this kind of events for the usual percolation, let's say, usually we need to assume on top that not that all points are connected together, but that all points in large connected components are connected together. There's only one giant connected component. So if I take any two big connected components, actually they are the same. That's what we usually mean in percolation theory. But here, each of my points, if it is in the interlacement, it is automatically in a giant connected component because it is just a random. Okay, so each point is in a giant connected component. So local uniqueness just means that all my points are connected together in this case. Okay. Is the definition clear? Yeah. Okay. So maybe before going to the results about that, let me say, why do we care about this local uniqueness event? And the reason is because it allows us to do some renormalization argument. So basically, you have a giant box, okay? And you want to show that the interlacement is somewhat everywhere in that box, in a certain sense, okay? And the idea is to subdivide this box into smaller boxes, okay, like this. And in this smaller grid, I will split it into groups of 4, okay? So let's say this is one group of 4. And then I have a second group of 4 here, okay? And then I'm going to assume that in each of my group of 4, I have local uniqueness, okay? So this means that here, all my trajectories that are here, they all touch each other, maybe not in the box, but in a twice bigger box, okay, not too far away. So I just have one connected component here, and then I also only have one connected component in the next one. So I'm asking that in each of this group, I have local uniqueness. Okay, and then if in each of these group I have local uniqueness, the point is that I have local uniqueness everywhere. So you need a bit more actually, because there's a problem here is that this trajectory here, okay, it's too big. Like I don't know if my trajectories on the first box and on the left box and on the right box are really connected together, because local uniqueness is only saying something about the trajectories inside each of these boxes, but not how do they compare with neighboring boxes, right? But so what I can assume to avoid this problem is that I can also take another group of 4 boxes, which is this middle group here. Okay, so I also assume additionally that I also have local uniqueness also in the middle here. And if I have local uniqueness in the middle, then it means that I need to have an extra trajectory that link my two trajectories here together. Okay, to make sure that I have local uniqueness and so that everything is indeed well connected together. Okay, so if I have local uniqueness at all of these scales, so let's say because I know that my probability of local uniqueness is very high, okay, so I can say, since my probability is so high, I can ask local uniqueness for everywhere at once, let's say, or at least for most of the box or something like that. Then it means that basically your interlacement on this renormalized lattice will be basically everywhere. It will be like a very supercritical percolation model, okay? Because the probability of local uniqueness is very high. Okay, and this is an argument that you can use a lot, and that has been used a lot. So, for instance, let me give you a few results that has been proven that way. So, for instance, if your interlacement is everywhere, what you can prove is that it is transient, and because basically it looks like ZD if you look at it from far away. Okay, and remember I'm in dimension larger than 3 here, so everything is transient. So this is still Raff and Shaposhnikov. And you can also show some kind of stability behavior, so that IU is stable under small perturbation. It means that if you remove a couple of trajectories from IU, or just a couple of points, using some extra randomness, let's say, then you still percolate. Okay, and this is because in my previous picture, if I remove a few of my squares here, since my interlacement is everywhere, I would still percolate because as long as I don't remove too many squares, right? As long as the thing that I remove is supercritical. Okay, and maybe in a way which is a bit less clear, another statement that you can prove is a statement about the Gaussian phi field. So you can prove that there exists an A such that the Gaussian, which is positive, such that the Gaussian phi field at this positive level percolates. Okay, and we proved this with Alexis Drevitz and Pierre-François Rodriguez in 18. Okay, I will also use that a lot, so let me abbreviate this as DPR. And this is a discrete GFF, okay, that was introduced in Pierre's talk. So this means that it's the Gaussian phi field, right? The Gaussian field with covariance the green function. If you forgot the definition, it will not come back too much, so it's not too bad. But if you remember the definition, you maybe remember also that Pierre was showing in his lecture that you add percolation above any negative level, okay? And actually using the interlacement and isomorphism theorems that relate the interlacement to the Gaussian phi field, you can show that for the discrete Gaussian phi field, you have percolation at positive level, not only at negative level. Okay, so this is some kind of PC smaller than a half statement or phase coexistent statement, if you want. And while I am at the GFF, let me show you a more recent result that was also proved using this local uniqueness for interlacement. So let me look at the 2-point function. But now I'm going to look at the 2-point function, not for the discrete GFF, but for the K-ball GFF. Okay, so remember this was this GFF where you didn't have only a Gaussian field at the vertices, but you were between the vertices, you were adding a full K-ball, right? And you had a phi X here, a phi Y here, and you were linking them by a Brownian bridge. Okay, you are extending your definition of the Gaussian phi field to the K-ball graph, which is this graph where I'm adding full edges between X and Y. Okay, and so if you look at K-ball GFF, what Pierre showed is that the critical point is 0. Okay, so here I'm looking. I am in the supercritical regime. I'm still assuming that A is positive. But I can approach the supercritical, the critical point by making A goes to 0. Okay, so this is a near critical result. And so the result is that this two-point function behave like distance between x and y to the -1, exponential minus, and then you have an explicit constant, which is pi over 6, 1 plus eta a square distance between x and y, and then you have a log correction compared to what you're used to in percolation, and this is true on Z3 if like my exponential dominate. Let's say if a square distance between x and y is large, and this is like a constant that depends on eta. Okay, so this is also DPR 22, and like we had the weaker version of this result in 22, and this full result is in 25. So this is really like the full near critical behavior of your two-point function in dimension 3. And this distance between x and y to the -1, you can rewrite it as the two-point function at criticality. And it's known that at criticality, this is exactly your two-point function. Okay, so it's just saying that my two-point function near criticality, I'm obviously at +8, sorry. Yeah, what's we don't talk. Is the same as my two-point function near critical times this exponential, or this stretch exponential if you want. But you know exactly what this stretch exponential is a squared distance between x and y. Okay, divided by log of a squared divided x over y. So this means that this a square is exactly your correlation length, or a to the -2 is your correlation length for your model. Okay, and the 2 is your nu for both of you now. So this is the full near critical result. I mean, for one bond. Okay, which is actually sharp, as we will see soon. Okay, so maybe let me go into the results now. So what is known about this local uniqueness? And it was already known. A lot was already known before, because as you saw, there are a lot of application that has already been done. So the first result is that, so I want to show that local uniqueness happen with high probability. So let me bound the probability that of its complement, that the local uniqueness do not happen. And this is like exponential minus c r to the 1/7. And this is Rav-Sapochnikov. And this is in all dimensions, larger than 3. Okay. So the constant here depend on u a priori. Okay, so you just say that this is some stretch exponential probability. And so actually, if you look at the proof, so this was good enough already to get application 1 and 2. Okay, application 1 and 2 didn't need more than that, just a stretch exponential decay of the percussion probability, because here u is fixed, so you don't need to know the dependency of u. But if you're interested in critical exponent, you want to know how does this depend on u, okay, this probability. And so actually, if you look at the proof and you adapt it a bit, you can get the following. You can get a u, okay? So the constant is actually cu, and now the constant do not depend on u anymore, okay? And so this, I mean, we prove it, and we're basically just following the proof and seeing where this leads us, that you can add a u. And this was useful to actually get free, okay, to get percolation at positive level for the Gaussian field to have some kind of explicit dependency. But this is not optimal, okay? This is just whatever comes out of the proof. But it was good enough. But actually, for this full near critical result 4, you need more. Okay, if you want to have here an optimal exponential decay, it means you need to have some kind of optimality also in your local uniqueness. And so, more precisely, what we proved is the following. So, still for this local uniqueness event, we prove that you can get a bond of this type. Okay, u r to the 1/3. This is on Z3. And so this is DPR 23. And in dimension 4, you get u r square over log r. And to some whatever power 2 over 10. Okay. So doesn't look much better. I mean, I have a different stretch exponential, right? But is it? I mean, if it's sharp, why not? Otherwise, it's why. The point is not the exact stretch exponential. The point is the dependency between U and R is now optimal. Okay, so why? So on Z3, we know that random walk intersect with high probability. Two random walks, they will always intersect at some point
Alexis?
on Z3. Yeah.
Yeah, can you hear me? Yeah.
Yeah.
What's the exponent? Is it 210? Is it 2/10?
Yeah, 2 over 10. Yeah, I mean, it doesn't matter at some constant.
Okay.
Yeah. Just whatever comes out of the proof. Yeah. And so in dimension 3, you know that random walk intersects with high probability. And so what this means is that you only need a constant number of trajectories for local uniqueness. Because if you have 2 points in your interlacement, so you have 2 random walk, okay, they will be intersected quite quickly by another random walk. If I just have, let's say, 10,000 random walk, then my 2 random walks. So if I just have 2 random walks and I try to connect them together, well, if I have like 10,000 tries and they will intersect quite likely one of the two, at some point I will find one random walk that managed to connect them together. Okay, so I just need a constant number of random walks to get local uniqueness with constant probability, let's say. And so, what is the number of trajectories for my random interlacement? I say that it was Poisson U capacity. This is what we saw. This was my Poisson point process, and my capacity is like U R to the d minus 2. Okay, add up to constant. And so it means that I need, and to have a chance to have local uniqueness, I need at least to have U R to the d minus 2, which is larger than a constant. Okay, so that I have at least many random walks, not just one. Okay, or not just 0, even if it was small. And so this is the correct scaling. And in dimension 3, you expect that this is enough because you just need a constant number of random walks to make your connection. Okay, so this means that what you expect from this heuristic is that the probability of local uniqueness should be like some function of U R to the d minus 2, at least on Z3, okay, where this previous heuristic works. Okay, and this is exactly what happens before and what happens above. So in dimension 3, you get UR. And in dimension 4, it should be even more, it should be the same, but maybe you lose some logs. Okay. So maybe, I mean, I don't know what these symbols mean, but you lose some log. Okay. Because then the 2 random walks, they will only intersect each other locally with like a probability which is 1 over log. Okay, instead of a probability which is constant. So you will lose some log, but it should still be, the main order should still be UR square. Okay, which is d minus 2 in dimension 4, and this is exactly what you see above. And then in higher dimension, this should be a different behavior. Okay, you don't expect that at this scale you already start to have local uniqueness. So this is the main improvement that you see above. That now you get it starts working at the correct scale. But of course, I mean, I was saying this 1/3 and 2 over 10, they are nothing. And so this is the point of the main theorem I wanted to mention today. So this theorem tells you that the probability of local uniqueness, or its complement, more precisely, decays like exponential minus, and you have an explicit constant, which in this case pi over 3, 1 minus eta. And then the correct decay is UR over log of UR. on Z3. And in Z4, you have worse results. You don't have the constant. And now it's square root of UR. And you have some log correction. Okay. So this is true. So this is true throughout what you want. So this is if UR is large. Okay, for the first one, and this one is if UR square is larger than this log. Okay, for the regime that you want up to log, let's say in dimension 4. And not only do you have this bond, but you also have some matching lower bound. Okay, so this is optimal. So you get the same, but with a 1 plus eta. Okay, like up to a small eta. For the in dimension 3 and in dimension 4, you lose some log. So the lower bound just becomes exponential minus c square root of u. Okay. So now this is optimal in dimension 3 and dimension 4, but still a bit of work to be done to. I mean, I expect that there is some log. I don't expect that you can get rid of the logs altogether. But what you can see in dimension 3 is that, okay, all these results before, they were always some kind of stretch exponential. And I mean, usually maybe from Bernoulli, you would expect actually to get some exponential decay. But there's a good reason you couldn't get exponential is that in dimension 3, it is actually not exponential. It's exponential R over log. Okay, so there was no chance to get exponential. But starting in dimension 4, it's actually exponential. Okay. I mean, if you forget the dependency on U, I mean, and you just look at the dependency in R of your probabilities. How much time do I have?
Can you hear me? Yeah, you have about 5 minutes.
Okay. So let me maybe skip a bit and let me just say two corollaries. This is together with Alexandre Evitz and Pierre-François Rodriguez, which is, well, we've improved local uniqueness. So what can you do with it? Every time until now we were improving local uniqueness, we were getting something new. And this is still the case. And so with this new, better local uniqueness, you can prove that in the whole subcritical regime, your 2-point function has the same kind of bound as before. Okay, but now for the upper bound. Yeah, so it's still a consequence of the isomorphism theorem. It's actually not a very hard consequence. And it's not a consequence really of local uniqueness. It's a consequence of something that I use in the proof of local uniqueness more precisely. But okay, I'm not going to go into detail. But you can get you can get the matching upper bound. So it matches exactly up to changing 1 minus eta to 1 plus eta to the bound that I was showing a couple of slides ago. And so this is maybe not too surprising that because based on everything you've seen before, but maybe another maybe more surprising result is that you can also get information on the random walk from that. So let's say on Z3, if you can get information on the capacity of the trace of a random walk. Okay, so you look at a random walk and you look at it in a ball of size R. Okay, and you look at how big is this random walk, and more precisely, how big is the capacity of this random walk. So this is something important to understand, like what is the intersection probability of random walk. And so if I look at, what I'm going to look at here is the probability that this capacity is much smaller than what it should be. Okay, so what is the role of T here? Okay, so the capacity, maybe let me write it here. So the capacity of BR is of order R. Okay, so I know that my capacity of my walk inside my ball, it's always smaller than the capacity of my ball, so it's smaller than R. Okay, but now I'm asking what is the probability that it's much smaller than the capacity of my ball? And for this, you have explicit large deviation bound, which tells you that this is exponential minus exponential pi over 3 So same pi over 3 as before. T. Okay, so it's this kind of double exponential. It's not really a double exponential because actually T can only be at most log R, because if your walk was just one line, T would be at most log R. So it's really a simple exponential in a sense. And the nice thing is that this is sharp, so you can prove the same, but with a plus eta also. Okay. You can also prove something in dimension 4 and so on. I'm not going to go into that. Also, I forgot to mention the corollary 1 was also on Z3. Everything's on Z3 because there are consequences of my result on Z3, and you have also some result on Z4 with some log correction, basically. And maybe let me just give you the idea of why can you prove this corollary true. So the idea is you say the following. You look at the probability that the interlacement intersect a random walk. So what is X here? And this is so let's say this is an independent random walk started at 0. Okay, independent of my interlacement. So I add a new random walk to my interlacement, and this, by my formula that was defining interlacement before, this is just the expectation of exponential minus u capacity of trace X intersected with PR. Okay. And so actually, what this is, when you see this, you see this is exactly the Laplace transform of my capacity of my walk. Okay. So if I have the Laplace transform of the capacity of my walk, it's not very hard to prove a large deviation bound as above. Okay, so that's easy. And so now, how do I get this Laplace transform? Well, I need to compute here my first probability. Okay, but this first probability, you can say, okay, but my random walk, it needs to avoid the interlacement. But now I know exactly with which probability does my random interlacement have local uniqueness. Okay, and so if it has local uniqueness, it will be very hard for the random walk to avoid the interlacement because the interlacement will be everywhere. Okay, and so I can use my local uniqueness. It's not really like that the proof is working, but let's say I can use my my local uniqueness to show that it's really hard for the walk to avoid the interlacement, which is everywhere, and so to get a good bound on this property on the left-hand side, and so on the Laplace transform, and so on the tail of the capacity. So you get information on the tail of your capacity of one random walk from this interlacement probability of local uniqueness. So yeah, thank you very much.
Okay, thank you, Alexis, for the great talk. Any questions, either online or in person? So I have one. I actually have two, but the first is this. So what you just described gives you the heuristic for the upper bound on this, right? But what about
that's correct. So the lower bound is actually easy, and that's why I didn't mention it. So how do you make? So you just need a good strategy, right, for the lower bound. And the good strategy for your random walk to have a small capacity is to do the following. You take a tube, okay, like that. So let's say it has size L. And then you ask, so L is much smaller than R, which is the size of the total box. And then I just ask for my random walk to leave my box while staying confined inside my tube. Okay. So if it does that, then I know that my capacity of my walk will be smaller than the capacity of my tube. Okay. And then I just need to tune my L so that the capacity of this tube is exactly R over T. And this gives me the lower bound. Okay, so the optimal strategy to reach this large deviation event is to stay in a tube which has exactly capacity R over T. So this is quite easy to prove. Yeah.
And my second question was, to obtain corollary 1, why did you? Maybe you said it, but I didn't understand. So where does this log a squared dxy come from? And also, I don't really see. So how do you connect it to the local uniqueness for the interlacement set?
Yeah. So okay. I mean, so okay. Maybe how do you connect it? I cannot go into the details now because it is going to the isomorphism between the Gaussian field and the interlacement, and you can rewrite your connecting probability or the probability to connect x and y as a probability for the interlacement. That actually the probability for the interlacement that you obtain is exactly a probability of this form. Okay, so you will again have this probability at the bottom when you use the isomorphism to try to reinterpret this in terms of interlacement. Okay, and so that's where the link with local uniqueness is. And why is there a log here? It's just because there's a log here.
Okay.
Yeah.
So I actually have one more, but does anyone else have a question? So could you just explain a little bit of the words of the proof for the local uniqueness, the last theorem you stated?
Yeah. Okay. So basically, I mean, local uniqueness is something about it's about intersection of random walks with interlacement. So basically, what you want to say, like it's not sufficient, but let's say it's a first step. Is you have your random interlacement, which is everywhere, and you add a new trajectory to your interlacement. Okay, and so when you add a new trajectory to your interlacement, you want to ask, is it still part of the same connected component or not? And so what you do is you run your random walk, okay, and then you arrive at a point where you're close to your interlacement. So you can go below. I'm in dimension 3. So maybe I can still go through while avoiding it, or maybe when I get close to my interlacement, I will actually touch my interlacement. Okay, and you want to control the probability that I avoid my interlacement when I get close to it, and so that you can control because you know the capacity of your interlacement, so you know exactly what is your intersection probability of a random walk with an interlacement. So every time you get somewhat close to an interlacement trajectory, you pay a cost to not be connected to it. Okay, and if you're connected to it, then you're part of the big giant connected component. Okay, and the main question is, but how many times do I get close to my interlacement? Because my interlacement, I mean, if U is large, it will be quite everywhere, right? So how many times do I get close to some trajectory of interlacement? Okay, because every time I get close enough to interlacement, I have a good chance to hit it. And so for this, you need some kind of first passage percolation result for interlacement. And this is actually the heart of the proof is the first passage percolation result for interlacement, to say that whatever my walk is doing, it will have to be many times close to my interlacement. Okay, so this is first passage percolation on a renormalized lattice, which counts how many times do I see my infinite cluster when I do a path from 0 to R. And the log here that you are asking about, it's exactly coming from the first passage percolation probability for the interlacement. So the probability that interlacements are well behaved, that is, I will see them many times along my random walk, actually has a log in this probability, and this is where it's coming from at the heart. Yeah.
Okay, so any other questions or Franco.
Yeah, thanks a lot for the great talk. So the question is very simple. What do you expect to be the behavior in higher dimensions? So what's the first scale at which you see local uniqueness?
So I expect, so let's say D larger than 5, you should want to have U to the half R larger than C. So basically, the probability should be exponential minus C U to the half R. It should still be exponential, okay? But you should have the mean field behavior. So it is larger than 4. 4 is the critical dimension for your model. And so in dimension 5 and higher, your mean field, and so you have this U to the half that appear. And in dimension 4, it's a critical dimension, and so I'm actually expecting, and I mean this is we're working on that currently, and I think it's working. Yeah, I am actually expecting to have this to be the correct probability. Okay, so it's a U to a half R, and the correction is square root of log, which is somewhere in between my two results, right? My two results, I have one which had a log, so you need to improve both results to get that. So yeah.
Okay, any other questions? If not, let's thank Alexis again.
Thank you.